Balancing redox equations. So in general, all chemical reactions are either redox, which means a transfer of electrons. For example, those would be single replacement, decomposition, combination, and combustion reactions, or all other reactions. So the redox or other reactions, this is where no transfer of electrons take place. And most double replacement are other reactions or acid-base reactions. How can you tell if it's a redox reaction or another type of reaction? Well, if the oxidation number of an element in a reactant species changes, any element, in that equation or that reaction, then that element must have undergone oxidation reduction. Therefore, the reaction as a whole must be a redox. So if you have any element in there changing oxidation numbers, it must be a redox equation. There are two ways to balance redox equations. The thing is, some redox equations are brutal to balance. If you can balance the redox equations the normal way, then absolutely by all means do it because it's much easier. But some redox reactions are so difficult that we have to come up with two other ways to balance it. One would be using oxidation number changes, and another would be using the half reactions. So we'll talk about how to use both of them, and you can really decide which one you would want to use. Using oxidation number changes. This is where we balance by comparing the increase and decrease in oxidation numbers. Let's go through some problems here, and these are the steps, so you're going to really need to memorize these steps as well. It's not as though you have to memorize one by one by one by one, but the more you do these problems, you just kind of get to know the process. So let's try with this equation. The first step is to assign oxidation numbers to all the atoms in the equation. Write those numbers above the atom. So we already did this in the previous section. Let's look at carbon. We know if it's all by itself, it's 0. Oxygen we know is 2 minus. Hydrogen we know is plus 1. So again, what would sulfur be? We know that these have to add up to be 0 in a neutral atom. So negative 2 times 4 is a negative 8. Plus 1 times 2 is a plus 2. So that means sulfur must be a minus 6. So we can just put that, it must be a plus 6. Plus 6, so we put that up there. So we have that side. Let's go over to the other side. Oxygen, we know, is a minus 2, and I really should put, I should put a minus 2 there. Now, two of those, a total charge of minus 4, so carbon must be a plus 4 to balance out. Rewrite that. Let's look at oxygen over here. Start with the ones we always know, oxygen, hydrogen, lone pairs, diatomics. So that's a minus 2. So that's going to be a total of minus 4. So that means sulfur must be a plus 4 in order to make it a 0. Plus water, this is going to be a minus 2, and hydrogen is a plus 1. Two of them, that makes it 0. So we just assign oxidation numbers to all the atoms in the equation. We wrote those above the atoms, and it all works out where all these neutral atoms are all going to add up to be 0. So let's go on to the next step. Alright, so now we identify which items are oxidized and which are reduced. Well, we're going to look to see which of the numbers change. So carbon changes from 0 to plus 4. Carbon went from 0 to plus 4. So if it went from 0 to plus 4, that means it must have lost electrons. So it lost electrons, it's oxidized. Let's look at hydrogen. So hydrogen here, plus 1. Hydrogen is plus 1. So nothing happened with hydrogen. Nothing happened with hydrogen, so that was not oxidized or reduced. Let's look at sulfur. Sulfur here is plus 6 on the reactants and plus 4. All right, so something happened there. So sulfur went from a plus 6 to a plus 4. Looked like to go to a smaller number, it must have been reduced. So we must have gained electrons, so that was reduced. What about oxygen? Oxygen, negative 2, negative 2, negative 2, negative 2. Oxygen stays the same. So here we have two items, carbon and sulfur, that underwent oxidation reduction. So we need to go on to the next step. I just erased the other charges just so I can see things a little better here. Now we go on to step 3. Use one bracketing line to connect the atoms that undergo oxidation and another line to connect those which undergo reduction. And we will write the oxidation number change at the end of each line. So let's go from C to C. So that went from a 0 to 4, so that was a +4. So if we're gaining positive charge, that means we are losing electrons, so that is oxidation. Now if we go from a sulfur to sulfur, a +6 to a +4, that means we are losing, or we're gaining a -2, so that is a reduction. We're gaining 2 electrons, that is reduction. Now in a balanced redox equation, the total increase in oxidation, number of species oxidized, must be balanced by the total decrease in the oxidation number of the species reduced. So increase must equal decrease. We don't have that here if we have a +4 in oxidation and a -2 in reduction. The next step will balance it. Next step will take care of that. We're going to make the total increase in oxidation number equal to the total decrease in oxidation number by using appropriate coefficients. So we're going to multiply those by a big number to balance everything out. So what this means is we're going to have to multiply these things by a lowest common multiple in order to get these, the +4 and the -2, equal to each other. So the -2, how can we get that equal to 4? Well, we will multiply it by 2. 4, so now we have 4 and 4, so that's equal to each other. Now we don't have to do anything to the carbon here, but oftentimes we will have to multiply this by something as well, as long as these two, the reduction and the oxidation are equal. That's what we care about. So in a sense, we might have multiplied that by 1. Keep that in mind. We multiplied this by 2. What do we do with this information? We multiplied this by 2. So we multiplied this sulfur by 2. So that means we're going to have to put the big coefficients there and multiply that by 2 as well. So we have to put a 2 here in front of the sulfur and a 2 here in front of the sulfur as well. So in front of all the sulfurs we have to do it. Unless if there was a little 2 here, we wouldn't have to do that. But there's not, it's just a single sulfur, so we're going to have to multiply a 2 by everything in front of that sulfur. And let's go on to the next step. Now there's a last step. Make sure that the equation is balanced for both atoms and charge. If necessary, finish balancing by inspection. So the charges are all okay. The atoms, let's see, carbon is good. 1 on this side, 1 on that side. Hydrogen, there's 4 here. There's only 2 here. So we're going to have to add a 2 here. Let's see and hope everything works out. Otherwise, it's going to be a heck of a bear of a problem to solve. Okay, so hydrogens are now balanced. Let's look at sulfur now. 2 sulfurs, sulfur should be because we just did it by a redox method. 2 sulfurs here, 2 sulfurs there, that's good. Now the biggie is oxygen. Is oxygen balanced? So there's 2, that's 8 oxygens there, and there's 2 plus 4, that's 6, and plus 2, 7, 8. So oxygen is balanced. We have a balanced equation. And it might seem like a lot of process just to balance an equation, but really, once you get used to doing this, it's much easier, and as well as also doing the half reactions, is much easier than just the trial and error inspection with these real bear of a problems.